Hi, my name is Guy Royse, and welcome to my talk on probabilistic data structures called Understanding Probabilistic Data Structures with 112,092 UFO Sightings. So obviously this is a rather whimsical title. I think UFOs are kind of fun and amusing, and they're just it's a fun topic. But I think probabilistic data structures are a really interesting topic, and odds are good you may not be familiar with them at all, but they're fascinating, fascinating things. And so we're going to go on a little journey, and I'm going to tell you what they are and give you some details of some, and so you can get your brain around how these things work and what they're good for, besides UFO sightings. So brief introduction. I said already my name is Guy Royse. I'm a developer advocate at Redis Labs, and you can follow me on Twitter at Guy Royse. You can check out all the code that I feel fit to publish on the internet at github.com/GuyRoyse. Code for a couple of the data structures that I'm talking about today will be in here. And of course, if you want to go out to my website and read my blog that I haven't posted to in, over 6 months, go out to guy.dev and check it out. So, 112,092. So this is a fun number. This is a big number. This is actually a surprisingly big number. This is the number of UFO sightings that I have to work with in my sample data. And this is the number of UFO sightings that was produced by the National UFO Research Center for, I think it's just for North America. It could just be for the U.S. It is the national one, so it's probably just for the U.S. 112,092, and this is over the course of from like 1950 on. So that's a lot of UFO sightings. And that's the data we have. I have to tip the hat to a man by the name of Timothy Renner, who actually wrote Python code to screen scrape all 112,092 UFO sightings so that they would be available for general data science and, just fun purposes. And so thanks, Tim. It's always appreciated. And the data, if we dig into the data, it's nothing particularly brilliant when we look at what the data itself is. It's tabular, rows and columns kind of data that we would see in any relational database, for example. It's got the summary of the UFO sighting. This is sort of a couple sentences describing the UFO sighting. In this case, three saucer-shaped ships. It's like Sioux seashells by the seashore, isn't it? High in the sky, metallic but no shine. Rather dull gray. They hovered overhead in a V formation. It includes the city and state of Salem and Oregon for this particular sighting. It's got a date timestamp in nice ISO 8601 date format. So this happened on September the 15th of 1950 at about 2 o'clock in the afternoon. And you see actually the 7 hours, so daylight savings time was in effect at the time too. The shape of the UFO sighting is a disc. The duration of that sighting was 15 minutes. There's a link to the New Forks website where you can go and read that report. And if you were to copy that link and click it, you could go and read this. And then there's the full text of it. It's got a little bit more going on. So like here, there's a note from the New Forks saying the witness indicates that the date above is approximate. And it's got the latitude and longitude of the city, which is something that Timothy added after the fact, having the city and state. So this is fun data, right? So this is the data we're going to play with as I explain to you what probabilistic data structures are. So what are probabilistic data structures? What the heck's a probabilistic data structure? Well, I did a quick developer survey on Twitter, so it's super scientific and ultra accurate. And 58% of people, of the 119 people who responded on my Twitter feed, had never heard of them. 22% had heard the term. So right now, we've got never heard of them, and I've heard the term, but that could mean I just read it in your tweet just now. We're already in 4 out of 5 developers have just merely heard of them and nothing more, or have never heard of them at all. We're into Trident dentist ratios here. It's 4 out of 5 developers, right? The other 20% are pretty evenly split between I know what they are and I've actually used them. And so if you don't know what they are and you're curious, don't feel bad. You're in pretty good company. I mean, personally, I didn't know what they were until about a year ago. And then I started looking at Redis and Redis's probabilistic data structures that are built in with it. And so to understand what a probabilistic data structure is, we need to look at sort of its mundane opposite, which I call, well, I don't call it this, everyone calls it this, deterministic data structures. These are the data structures that you use all the time. If you have used an array list in JavaScript, in Java, or if you've used some sort of sets, or linked lists, arrays, graphs, tables, trees, stacks, queues. If you've used any of these things, you have used a deterministic data structure. And if you've written software, you've used these, right? And they have different characteristics, and we pick these different deterministic data structures for different reasons. Like, tables, or hash tables, have particular characteristics that make them performant, but they're a little more wasteful in space. Linked lists are very compact in space, but they're difficult. They're cheap to modify, but traversing them is expensive. So because you have to walk the list to find the thing. Arrays give you very fast access. They have different features and capabilities, but and we pick them for those reasons. But the thing that they definitely do is that when I put something into a list or in an array or a queue, I expect to get it back out and get it back out faithfully and with full fidelity. That's why they're deterministic. It does the same thing every time. It is deterministic what will happen. Deterministic data structures. We're going to look at one in detail. We're going to look at hash tables. And the reason we're going to look at hash tables in detail is because the way hash tables use the hashing functions is very similar to how the probabilistic data structures we're going to look at all use hashing functions as well. And so understanding this idea is key to understanding the later probabilistic data structures. Hash table is a wonderful key value store that we use all the time. Redis has one, right? Java has one. JavaScript objects are key value pairs. We see these in lots of languages. And the idea is hey, here's the key. You look it up in this dictionary-like structure, and you get the value out. And so, this is kind of this visual representation here we have on screen is kind of how we view these things in our brains. It's just a table it's a lookup table, right? And so here's our data, one of our UFO sightings as a hash table. Hash tables are called hash tables because they use a hashing function. And you're probably familiar with hashing functions, but just to be very precise here, we're using hashing functions to take arbitrary data. In this case, we've got a series of bytes. Those bytes actually, if we look them up in ASCII, spell out the word Scully. And we have a seed. And both of these, and this is just a random number that we want to use the same one every time. And when we feed the data and the seed into the hashing function, we get a unique number out, or sufficiently unique. Like this could be a 32-bit number, or maybe even a 64-bit number. And it's sort of, hashing functions take a big pile of data and they squash it down into a single number. And so that data could be a 2 gigabyte document. It could be the string city. But regardless, they get squashed down into this 32-bit number or a 16-bit number. I use smaller numbers later in the examples just so they fit on the screen. And so that's what hashing functions do. And you may be thinking hashing functions and you're thinking, oh, like cryptographic hashing, like SHA. It's like, well, no. Yes, but no. Those will work. But one of the things we're doing here for data structures is we want them to be fast. And so there are other types of hashing functions that are not cryptographically secure. You can reverse engineer them. They're fast, and perhaps figure out things and figure out patterns and stuff. And so they're not secure, but they're good for this sort of data structure. Things like murmur hashes is one that I use in all my example code. These sorts of hashing functions are designed for speed and uniqueness, but not designed to be secure. So you take your data, you take your seed, you cram it into that hashing function, and out comes a number. And that number is used in a hash table to figure out what index you're going to do. So you set up a hash table, and so you set up an array, indexed 0 to however long you want that array to be. And that is an array of buckets that are going to hold your value. Specifically, it's an array of linked lists, typically. And so when we go to add something to this hash table, let's say and we want to put it under the key city, then we put the word city into the hash function along with our seed, which needs to stay the same, and that'll give us a big unique number. And then we do a modulus to constrain that number down to the size of our index. And here we're going from 0 to 9, so it's 10. So we do a modulus of 10, we get a 1, and so then we put the value in index 1. So city, when we add the value Salem, shows up here in position 1. If we then go to add state, we run state through the hashing function, and this time we get a number that ends in 4, and so it goes into index 4, and we put Oregon into position 4. Now what can happen, and I mentioned linked lists earlier, and this is why. You can get a collision. So we put shape in, and we get 1 again through the hash and the modulus. And so what we do is we store in the bucket the linked list. And so Salem is in there first, and it's got its associated key value, shape, or perhaps the actual hash value without the modulus. And then the next one is disk. And so when we go to read that, we can say, well, hey, we're looking for shape. And it will say that's in position 1, and then it'll walk the list in position 1 until it finds something that matches the word shape. And so this is how we deal with hash collisions. We keep a list. And obviously, if your hash table is too short for the amount of, it doesn't have a big enough index for the amount of data that you want to put into it, you're going to get more collisions, and then it's more traversals along this list, and that decreases the performance. Whereas if you make the hash table too big, then you're wasting a lot of space because the hash table is mostly empty space. So there's a balance in allocating that, and that's usually hidden from us. We just create a hash and go on about our lives. But that's what's happening internally. And so we do a lot of these things, and we fill this hash table up, and so we can see our hash table's got a collision. It's about half full, and we've got all the stuff in there. And so when we go to read from it, it's exactly the same. I think I've talked about reading already. Put in city and modulus of 10, and we walk through index of 1. We go find Salem, get the city back. So this is how a hash table works. The key thing is that we're taking the key that we're using to look at, the key and the key value pair, and we turn it into a number, and then we modulus that to get an index. So that's a pattern that we use, and that pattern recurs throughout this talk. So it's important to really get your head around that idea. Now, all these data structures that we look at, there are time and space complexity trade-offs. What do I mean when I say time and space complexity trade-offs? Some are fast, and some are slow, and some, to access a linked list, it's time expensive. So it's got a time complexity of O of n, and being up to the length of the list, because you've got to walk that linked list to get to the one you care about. But they're very compact. Conversely, a hash table can have a lot of empty space in it, but they have a constant time complexity to access, because, assuming your linked lists aren't too long within the buckets, because you hash the data and you go straight to that index. Arrays, for example, are very fast access, because you just go right to where you want to go, and they're also very compact of space. Finding things in an array, you have to walk through the data again, like a linked list. So so you're often making these trade-offs on your data structures of, do I want to conserve space or do I want to conserve time? But this isn't actually the whole story. There's a little bit more to it. And that's that the time and space complexity can sometimes be within itself. And so, for example, arrays have a space complexity of, they're very fast to access, even though they're slow to search. But in space terms, they're compact, except if you need to resize them, then it's really expensive. Whereas, like, resizing a linked list, you don't need to worry about that. You just add another thing to the list. It's no big deal. And so the complexity is more than just a trade-off. There's, like, space complexities within themselves. And they'll be good at one aspect of dealing with space, or one aspect of time, but another operation will be slow. And so you're also making those sorts of trade-offs. And there's actually another trade-off that you can make, and that is accuracy complexity. Instead of having deterministic data structures where you have time and space are your two variables, you can also say, Well, what kind of performance could I get if this thing was only 99% accurate? What if it lied to me 1% of the time? What would my performance characteristics look like then? Because that might be a good trade-off. If I've got a billion rows, that performance boost was well worth it, or that space savings boost. Can I save space in exchange for reducing the accuracy of my results? Can I build a data structure, or if I put something into it, I might not get it back all the time? That's an interesting thought, isn't it? Well, that's in essence what a probabilistic data structure is. They are data structures that have a accuracy trade-off that you're making. And usually you're sacrificing accuracy to get, and often capabilities, to get improved performance and compactness of storage space. Here's an example of what is technically a probabilistic data structure, but is in truth a terrible idea that you should never do. You could do hash tables without the chaining, without the linked list. And so what they would do is they would just be an index, and then the data, a string, basically. And so when you come in and say, I want to shove the city Salem into the list, you get a modulus of 10, it says index 1, you put it in position 1. It's great, right? Works like a champ. Still a bad idea. Then we go to put shape in. And before, when we put shape in, which also has a modulus of 1, because there's a collision here, it would create an entry in the array list, and then, or in the linked list, and then we just walk that list. But here, it replaces it. And so now index 1 contains disk and no longer contains Salem. Salem is gone. The data is no longer available. And so that when you go to read from it, OMG, what have I done? Exactly. I asked for city, and I get disk back. And so this is in some ways sort of a simplistic probabilistic data structure that says, well, you can get stuff back most of the time, but not always. Now, you might be thinking, this is a little crazy, and I would certainly never do this, and you shouldn't do this. This does say, oh my God, what have I done at the top of the slide, so please don't do this. But there is a probabilistic data structure in a sense that you've used many times and are very familiar with, and that is the lowly JPEG, the humble JPEG. This is a picture of the Devil's Tower. It's quite a beautiful picture. It was, in my mind, made famous by the movie Close Encounters of the Third Kind. And in this wonderful picture, you've got all these blue pixels at the top. And those blue pixels are next to each other. And there's probably some pixels that are slightly a different shade of blue and slightly yet another shade of blue. And so they're not quite the same. And the data we're getting back about what those pixels are in the JPEG are wrong because we've compressed it. We've done a lossy compression to make this JPEG take up less space. And the trade-off there is lossy but good enough. And that's what we use our probabilistic data structures for. Things that can be lossy, but they're good enough. A lot of the probabilistic data structures that are out there can be thought of as sets with peculiar properties. Maybe they don't have the full range of capabilities that you typically have with a set, or maybe they are inaccurate in some way. And all the ones we're going to look at today are specifically are variations on a set. And so here we've got a set of shapes, totally arbitrary and not picked from Redis's logo, of a star, a square, a circle, and a triangle. And sets, you can do things. You can add to them. You can add things to the set. I could add, say, a pentagon to this, or a nonagon maybe. I could remove the circle. I could get things out of the set. I could do a union of couple sets, or an intersection, or a difference. All the stuff that set theory lets you do. I could check them for membership and get the cardinality of a set. And a lot of these probabilistic data structures will only let you do a subset of the set operations. So let's talk a little bit about some of the things that you can query around. The probabilistic data structures allow you to do. One of them is you can build probabilistic data structures to check for membership. Membership's simple. Is the thing in the set? This is a really easy idea. A member is any one of the distinct objects that make up a set. Is the square in the set? Yes. Yes, it is. Is the pentagon in the set? No. No, it isn't. Easy peasy, right? Membership. Is it in there or not? Bloom filters are a probabilistic data structure that do this, that we're going to look at once we're done talking about sets. Cardinality, which that's a fancy word for counting how many things are in the set. Our set has 4 things. It's the number of members. There's a star, a square, a circle, and a triangle. It's got a cardinality of 4. If we added a pentagon to this, it would have a cardinality of 5. If we removed the square, it would have a cardinality of 3. We're just counting the number of things in the set. Again, this isn't a complicated idea. Cardinality is kind of a, it's a technical term to describe the counting the number of things in it. This is a concept we all understand. Frequency is a little different. It answers how many of each thing is in a set. So you could add the square to the set twice, and the cardinality would not count the square twice. It would only count it once. Whereas a frequency would show you that there are 5 stars, 4 squares, 6 circles, and 3 triangles in the set. And so frequency allows us to, well, look at, how common things are in a set. It lets us count things within a set. And so that's another common thing that we look at. Rank is kind of related to frequency because it keeps track of, like, you can derive rank if you have frequency, but you can just look at rank, which is what order are these in based on their frequency, right? And so here we have, our circle, our square, our triangle, and our star are ranked based on 1st, 2nd, 3rd, and 4th. And so you can look at this and say, well, give me the top 2 items in here, or give me all the items in the set in rank order. And so that's another thing that we can derive from sets, is rank. And I have to be honest, this is my favorite picture in all the pictures in my slide. Similarity is an operation you can do between sets. You can take 2 sets and say, how similar are these sets? Is this thing like the other things? And so here we've got some sets, and we could compare or measure the difference between these sets. And we'll go into details when we talk about min-hash of one mechanism to compare sets called a Jacquard similarity. Here we've got just pictures of sets, so one of them's full, some of them are missing elements. And we could compare how similar these sets are to each other. So when it comes to using probabilistic data structures, there's a lot of choices. There's a lot of probabilistic data structures you can choose from. We're going to talk about 3 today, the 3 that are highlighted in blue. Bloom filter, heavy keeper, and min-hash. Bloom filters are for checking membership. Heavy keepers will return rank, and min-hash will give you similarity. There are lots of others. Cuckoo filters also do membership, but they're a little more capable than Bloom filters, but they're a little more complex too. Hyperlog log lets you do cardinality, and actually it's kind of cool. Hyperlog log will store, you can count the number of atoms in the universe and not store in more than 12K. Kind of amazing. Count sketch and count min sketch are determined frequency. Q and T digest I haven't looked at very carefully, but they're ranking ones. We're going to look at heavy keeper and heavy guardians, which is similar. And sim-hash is a variation of min-hash. And some of these probabilistic data structures are available in Redis. And so if they're available in Redis, they've got the little red dagger on them. And if they got the double red dagger, which is just hyperlog log, they're actually available in just core base Redis. The Bloom filter, the Cuckoo filter, and the Heavy Keeper are actually part of Redis Bloom, which is a module that Redis has available. Modules? Did he say modules? What's a module, guy? A module is sort of like a plugin that you can extend Redis with. And we've got a whole host of them available, and they're all out there, and they're open source, and you can download them and play with them and use them for your commercial and non-commercial purposes. They're open source. They're the Redis source available license is specifically the license they're using. And we've got stuff for Gears, which lets you run Python code, Redis JSON, which lets you do JSON data types, time series, search, Redis Graph, which is one of my personal favorites, Redis AI is a model hosting server, and the one we would care about today, Bloom filters, which is the little stacked thing on the far right there. And so you can go download these, and I heartily encourage you to play with them. So first we're going to talk about Bloom filters and how they work. And they work, well, before I talk about how they work, I want to talk about what their limitations are. What's a bloom filter? Bloom filter tests for membership, and it can answer two things. You can say, no, this thing is not in the set, or it can say, probably it is in the set, which is a little weird. It can say no or probably. They are, when created, a fixed size in memory. So once you create them, they will get no bigger. And they are wicked fast. The fixed size is really important because if you make a bloom filter that's a fixed size and then you overfill it, it will start returning more and more false positives until all it says is probably, and it never says no. So you want to make sure that when you make a bloom filter, you make it sufficiently large. How does a bloom filter work? Well, let's look at the parts first. So a bloom filter has a series of hash seeds and a hash function. And so you got these hash functions with seeds. I'm using 3. You can use various amounts, just however you want to set your bloom filter up. I'm using 3 because it fits on the screen. And so you see here we've got our seed numbers, we've got our hash function. We're probably going to put some data into here and get some numbers out, aren't we? The other part we have is the bit array. It's a fixed width bit array. It is literally bits. And so here I've got a width of 10 bits. And so the bloom filter takes up 10 bits of memory, plus the memory required to store their hash keys, the seeds for the hash functions. And that's it. Those are the parts. That's all you've got. The array and the seeds. And the array is set initially to all zeros. And as we add things to the bloom filter, they will be turned into ones. So how does that work? Well, let's take an example here of a UFO sighting, Megatron in the bushes. This is actually probably my favorite of all the UFO sightings that I've perused. These guys down in, I think in Arizona somewhere, heard a sound that sounded like Megatron transforming, that sound that the Transformers made back in the 80s cartoon. And they thought they heard that in the bushes and then saw some UFOs. Sure. Okay. So we take that data and we run it through our hashing functions with our seeds. And we're going to get 3 different numbers, right? Because we got 3 different seeds. And we take those numbers and we do a modulus operation, just like we did with the hash table, equal to the width of our bit array, just like we did for the size of our array for the hash table. So we've got 10 bits, and so we do a modulus of 10, which means we look at the last digit here. We get a 5, a 0, and a 6. And so we look at 5, 0, and 6 in the bloom filter, and we set them to 1s. Now it is stored in the bloom filter. Megatron in the bushes, the data is gone. Right? We have destroyed it. We've turned it into hashes, which we turned into indexes, which we turned into bits. And so it is just, you cannot go ask the bloom filter, hey, give me a list of all the things you've added to me. They're gone. It's just not available. However, if we want to read from them, if we want to check membership, we take Megatron in the bushes, run it through the same process with the same seeds and we get the same hash results, we get the same indexes, and then we read and we see that they're all 1s. And since they're all 1s, it's probably in the bloom filter. It's probably part of the set. And that's how we read and write to a bloom filter. Let's write something else to a bloom filter. This one is a UFO sighting that happened right here in Columbus, Ohio. I seen a UFO when I was about 13 years old. All in uppercase. It was actually all in uppercase in the original data. We run that through, and we ultimately get the numbers, the indexes 2, 1, and 6. Now, 2 and 1 haven't been used before, and so we set those to a 1. However, 6 has been used before, and so we just leave it alone. It's already a 1. We don't need to do anything with it. So we've got a collision, but because we have multiple hash functions, we don't have a complete collision. They don't completely override. And when we go to read it, we get those same numbers out, and we go look at 2, 1, and 6, and they all come back as 1s, and it's great. It says it's probably in there. However, if we have a total collision, then we have a little bit of a problem, don't we? So here, investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. When we run that through, well, it turns out we have bits 0, 1, and 6. And when we look, those have all been set. Some of them have been set by Megatron, and some were by the guy who had seen a UFO here in Columbus. And but it doesn't matter because they're all set. And so when we go to add this to the bloom filter, it doesn't change the state of the filter. And when we go to read it, it says, yes, that's probably in there. But there's no evidence that it was or wasn't there, right? Kind of like UFOs themselves sometimes, it seems. If we hadn't added it, it also would have said the same thing when we went to read it. And so that would be a false positive. But if we had added it, that it's not a false positive. Which is why I can only say probably, because you'll get these collisions. And this is why, for example, when a bloom filter starts to fill up, these collisions become more likely. You can mitigate that by making your bloom filter bigger, making the bit array wider. You can mitigate the impact of collisions by increasing the number of hashes. If you decrease the number of hashes, you get less collisions, but they're more impactful. And so there's a lot of juggling that you have to do to figure out what these values should be. And you might be wondering, how do I figure out what these values should be? Well, there's a formula for that. Just do this easy math right here, and you're good, right? This actually isn't as terrible as it looks. You can use these two formulas by basically saying some of these things are things you know. So n is the number of items. You know how many items you want to store in your bloom filter. I want to store 1,000 items in here. Okay. M is the number of bits. Well, that's something you need to figure out. But if you pick a number of bits and a number of items, it can compute an optimal number of hashes using the bottom formula. And with that, then you compute P, which is the false positive rate. And look at that positive rate and say, hey, you just pick a number of bits and say, let's go 1,000 items. Let's go 500 bits. Let's see what happens. You do the math and you get a probability and you say, I'm not happy with this number, or I'm happy with it. And if you're not happy with it or you're happy with it, adjust the number of bits accordingly and recompute until you hone into the area that the value you care about. So it's not that terrible, really. The even easier way, of course, would be to just use a Redis bloom filter. With Redis bloom, you just say BF reserve. You give it a key name. You give it the desired error rate. I want 0.5% of acceptable error, and I want to store 100 items. And it does all that math for you. It figures it out. Using the bloom filter in Redis is super easy. You got BF add, which adds a thing to the bloom filter. You can see there it returns a 1 when we add a disk. Called BF add to add light, returns a 1 because it's modified the state of the bloom filter. There's also BF mad, multiple add. And when we add light and teardrops, light's already been added. And so the bloom filter should return that's found. And so you see here we get an integer result of 0 and 1. 0 because light is in the filter already, and 1 because teardrop isn't. To actually make use of the bloom filter to check for membership, you call BF exists. And again, passing in your key and then just the item and return 1 or 0. Does this exist in the bloom filter or not? And there's a mexists, M exists, a multiple exists, which just does the same thing but lets you check for multiple things in one call. So that's bloom filter. You might be wondering what you could use those for. I think the coolest use case for bloom filters excuse me. I think the coolest use case for bloom filters is I think it's a gatekeeper for expensive processes, right? So you've got some data that you need to perform an expensive operation on. You can put that data into a bloom filter to say that I've done this before. And then you can check and see, have I done this before, yes or no? If it says no, then go ahead and do it. If it says yes, then check to make sure and then do it. Another good example would be I need to query to see if a username is in existence. If you've got like 1,000 users, select count star from users where name equals, foobar is perfectly valid, and it will just tell you, is this taken or not? But if you've got 1 billion users because you're, say, Facebook or Google or something, then a bloom filter is a way better way to do this because you can just add them to there and they say, is this taken or not? Every user gets put in that bloom filter, and if that username is taken, it will say probably. If the username's not, you can go ahead and safely create it. And if it lies and gives you a false positive and says this username's taken even though it's not, then someone doesn't get to use the username they want to use 0.5% of the time. And that's a reasonable trade-off to get the scale and the speed that you want. So, next one, minhash. Minhash is not part of Redis, but I think it's really neat. It lets you do similarity in sets. It determines set similarity between documents specifically. So if you've got two documents, you want to see how similar they are. Say maybe to detect plagiarism, or maybe to see whether you should reindex it or not if you're a web crawler for like a search engine. And you can do that using compare documents or any sets using a thing called Jacquard similarity. So here we have Skulder and Molly. And Skulder on the left here is from, he's got a list of places where he's seen UFO sightings. And Molly has got a list of places where she's seen UFO sightings. And so there's, they've got two sets here. And to calculate the Jacquard similarity, we just take the intersection of those two sets, the cardinality of the intersection of those two sets, the count, how many are in there, which in this case is New Mexico and Ohio, and divide it by the union. That'd be the total number of states in these sets. So if we count these up, we get 10 things in the union. The cardinality of the union is 10. The cardinality of the intersection is 2. And so you take 2 divided by 10, and they are 20% similar, which if you look at it kind of makes sense visually, right? It's just the count of the intersection divided the count of the union. All there is to it. But if you did this with documents, it kind of wouldn't work very well, right? If you just took every word in the document and added it to a set and compared two documents, you would just verify that they're English. You wouldn't verify that they are anything more than that, because we're all using the same words. We're just not using them in the same orders and combinations, right? And so a way to turn a document into a better set is to do a thing called shingling. What shingling does is it grabs a trigram from the document, a group of 3 words, and walks along the document, doesn't. So the first one is we notice 2, and so that gets added to the set. And then we go one word over, like a shingle, right? They're layered like shingles on a house. And notice 2R is the next trigram. 2R left, and so we start building up our set this way until we get all the way to the bottom with a bright glow. We notice to our left, further off into the mountains, a bright glow. And so this turns this document into a set that you could actually do a comparison against. But, when you go to do that comparison, it's really, it works, right? We sit here, we do the intersection of the union, and we get a 7 in the intersection and an 11 in the union. Skinner wants to make sure that Skulder and Molly are telling the same story, and so he compares their documents using this technique and sees that they're 0.636 or 63.6% similar. So they're telling basically the same story with some variations of details. And this is fine if you're just comparing two documents, but there's 2 problems with this, and they both impact the performance. One is these documents could be really big, right? They could be hundreds of pages, thousands of words. These could be novels that we're comparing. They could be 80,000 words. It's a lot of words, and you're doing string comparison against both of these, and it's just inefficient. And if you're doing something where you're trying to find more documents, and you've got one document, you're comparing it against a bunch of documents, or you're comparing a group of documents against each other to measure their similarity, then the network effect causes those to, that performance to get slow quick. And so, is there a way to make this faster? Yes, there is, and that's where minhash comes in. Minhash is a way of turning this set into a collection of numbers. And so once again, we're using hashes, and we've got multiple hashes with multiple seeds. And in this case, we've got 3 hashes with 3 seeds. And we take the entire set of trigrams, the shingled document, and we create a number for each entry in that set. And so we notice 2 comes out the number 325, 316, and 991. Notice 2R comes out to the next column of numbers, and so on. And so we end up with a set of numbers for each hash, corresponding to each entry in the original set. From those, we take the smallest number, the minimum hash, the min hash, and we make a set of 3 items. And this is sort of like a signature for the document. And so we have 3 numbers here because we have 3 hash functions. If we had 5 hash functions, we'd have 5 numbers. And so here we calculate Scalder's min hash, and we get these numbers on the right. Do the same thing for Molly, and we get similar but not identical numbers. And then we can take these numbers, and we can store them and use them for future reference. We take these numbers and we do the Jacquard similarity of the minimum hashes. And here we get a Jacquard similarity of 50%. They're half the same. Given that we only have 3 hash functions, this greatly reduces our resolution. If we wanted to have a more finely resolved answer to this, we could increase the number of hash functions and we could get a higher resolution out of this. But then, of course, that takes longer to do, and so there's always a trade-off of how many hash functions you want versus speed. You know, always a trade-off. There's always a trade-off, right? And so this explains why using just the raw documents, we can get about a 2/3 similarity versus a 50% similarity. Cool. Min hashes are really interesting, and I've coded one up in the repository on my GitHub in Java and in JavaScript. For the Bloom filter, I have a JavaScript and a C# implementation, so you can go check those out if you want to see how they work in greater detail. The last probabilistic data structure is top K, which is actually heavy keeper. Top K is a problem. It's a ranking problem. Heavy keeper is the part of a probabilistic data structure that keeps heavy things and throws away light things. When we combine that with a min hash, or not a min hash, a min heap, we have a thing called top K. So what's top K do? It ranks. It ranks the top K items. So if you want the 5 coolest ways to get people to click on your links using clickbait, then you would be ranking it and getting a top K. It'd be the top 5. And top K uses the heavy keeper, which we're going to go into detail in, and the min heap, which is not a probabilistic data structure at all. It's a heap. In concert to solve this top K problem. The min heap stores, in our example, we're going to be storing the shapes of UFOs and their counts. And so here we've got the top 5 most common: disk, sky, light, dark, and object, and their counts underneath. Anything that's below the 54 just gets thrown away. We're not going to keep track of it. We want the top 5. The heavy keeper itself is a lot more complicated than the heap. And it again has these hash functions with these seeds. And it's got this these buckets that look a lot like a hash table. And they store, in addition, they don't store the value. What they store is the hash of the value and the number and a count. And that hash is the result of the hashing function. The count is how many times it's encountered it. If we have a brand new heavy keeper, our hashes are all null because nothing's been put in there. Our counts are all 0 because nothing's been put in there. So when we go to add something, let's add the value object. That's a very popular word to describe a UFO, a popular shape. We take that object, we run it through our hashing functions, and we get a number. I've got 3 numbers here, 5062, 3111, and 1442. And then we do a modulus equal to the width of our buckets. How wide is this? These hashes. And just like we did with the Bloom filter, just like we did with the hash table, once again we're modulusing it to get an index. And then in that index, we update them. We put the hash value we got, the full number. This is probably a 32-bit number. I'm using smaller ones because they're easier to show on screen. And we increment the count by 0, from 0 to 1. So since the hash is null and the count is 0, we just plop it in there. And so now we have the value object in here. If we decide to add object a second time, we come into the same indexes. The hash value is the same, and so the rule is if the hash value is the same, we increment the count by 1. So we now object's in there twice. Now if we go to query the count, we can say, hey object, hey heavy keeper, how many values for objects do you have? And we'll go out and we'll once again get the same hashes, get the same indexes, go out and find the same values, and we'll find that they're all 2s. And so we'll say, hey, it's 2, which is correct. So far, heavy keeper is counting accurately. If you add a different value, something interesting can happen. So here we're going to add the word light. And the first and second hash functions get different indexes, and so they just follow the rule of there was nothing there, now there is, set the 0 to 1, put the value in there. But the third one ended up with an index that takes it to something, to an occupied index, right? So 1442 is there with a value of 2. So what do we do? Well, what we do is we roll the dice and see whether we're going to decrement it. This adding light to this may eventually decay it or kick out that value because it's not heavy. It's heavy keeper. It may not keep the lighter things. So what we do is we do a little bit of math to determine that probability. The probability of decay is P equals B, which is a rate of decay that we select, to the power of negative C, which is what the value of count is, in our case 2. And so B is arbitrary and should be greater than 1, but also about 1. So 1.05, 1.01, the bigger the number, the more likely of decay. Then when we go to compute this, in this case we end up with 0.907. So this is a 90.7% chance of it decaying. So we roll the dice. Did we get 90.7 or lower? Yes, we did. Then decay it. Decrement the count by 1. What's interesting here is the bigger that C is, the much smaller P becomes, because we're to the power of a negative number. If that count was 1,000, this would be a much, much smaller number, and so it would be much less likely to decay. And that's how the heavy keeper keeps things that are heavy. And we call these heavy things and these little things, you get these flows coming in where there's some are small and some are big. We call them elephant flows and mice flows, or mouse flows. And so elephants tend to be hard to move around and stay where they're at and don't get dislodged. And the mice tend to be scurry about and scatter easily. And so, but a mouse, if all of a sudden the data started accumulating for it, could grow big and dislodge an elephant. So it keeps the heavier things, and they're constantly, it's like they're fighting constantly and pushing them each other out of the hash. So we're going to go ahead and say decay has occurred, because that's pretty likely, 90.7% chance. And so our third row there gets knocked down to 1. So 1442, position 2, has a 1. But that's fine. That's not a big deal, because we still have these values in other places. So if we go and query light after the decay, we go and find a count of 1 and a count of 1 in the first two arrays, in the first two rows here, but the third row doesn't have an entry for it. It goes in and finds the index, but the index has a mismatched hash. It's not 1442, it's 1352, and so it doesn't read that one. But the rule for returning the count is take the maximum of all the counts. And so null is 0, it's not there, so it just looks at the first two rows and says, yep, there's one thing, it's light. There's one light in there. And so it still works. These extra rows preserve that content, and much the same way that multiple hashes in a Bloom filter preserves values when there are collisions. We could query the count of object, and this is interesting too, because this returns 3 values, but they're not the same now. And so the rule is that you take the largest of all those, and that's what the count is. And so the result of this is that we're still able to get an accurate object count. We're still able to get an accurate light count. But over time, these numbers can be whittled down. And so one of the guarantees of a heavy keeper is the count is never more than what's real, but is often less than what's real, because they get whittled away. But that's fine, because we're not using it to count. It's not a reliable way of counting. What is a reliable way of doing is ranking. And it does that by shoving them on the min heap every single time you add something. You add something, you get the count back, and then you look at it and say, is this count greater than the smallest thing on the min heap? If it is, put it there instead. And then recalculate the min heap. We do that each time. And so that allows the min heap to just contain the top 5 items, and so we can just go to the min heap and get the top 5 items in order. Redis has a top K implementation that does this internally. To set up a top K, we say top K.reserve. We give it a key. We set the number of hashes that we want. Or I'm sorry, the number is the number of the topness, the K. We want to keep track of the top 3 items, let's say. We set a width for how wide those indexes are, how wide that array is. We set a depth for the number of hashes, top to bottom. And then we set a decay rate. And here, Redis does it using the reciprocal of the number we used in the other example. So here, 0.9 is going to turn into 1 point something small. But it's otherwise the same idea. And so once we have a top K reserved, we can use it. We can add to it by saying, add a disk shape, add a disk in a teardrop shape, add a disk in a teardrop shape. So we have 3 disks, 2 teardrops, and 1 light in our top K. When we query it, we can say, hey, is disk in the top K? And it'll look in that min heap and say, is it in here? And if it is, it'll say, yes, it's in the top K. You're good to go. And otherwise, it'll return 0. No, it's not. We want to get a count. We can say top K.count and pass in a type, and it will return the count from the heavy keeper. And we can also get a list of our top K items by calling top K.list. And so Redis makes using heavy keepers and min heaps together to solve top K really, really simple. So some resources that you might want to look at if you're interested in learning more about probabilistic data structures. Bloom filters, by example, is a fantastic example. It shows graphically how they work. It's really good. The Bloom filter calculator will do the math that I showed you earlier for figuring out how wide to make your Bloom filters. The min hash tutorial gives a great understanding of how min hash works. Heavy Keeper, an accurate algorithm for finding top K elephant flows. This is a white paper. It's a little more dense and difficult to navigate, but it totally is accessible. This is how I learned how top K works. The UFO Sightings dataset by Timothy Renner is out on data.world. If you want to play around with this dataset for other purposes, please have at it. Might be fun to do like Markov chains to generate UFO sightings and that kind of stuff. The National UFO Reporting Center is the original source of this data, the New Fork. So go check them out if you want to have some entertaining reading. And of course, I can't neglect the Redis resources. If you want to check out Redis Bloom, go to redisbloom.io. And if you're looking for a good understanding of how top K works in Redis, one of my peers has written a article called Meet Top K that's on the Redis Labs blog. So, and of course, all these slides and all my sample code can be found here at GitHub. So you may want to pause the video and go check out what's available there. And that's what I've got very much. Thank you very much. My name's Guy Royse, and thanks for watching my talk.